All right, how are we doing on sound? Good? Yeah, so this is the next of the forward-looking talks. I was assigned to speak about what do we want to see, water worlds and rocky planets. I don't have as many awesome pictures as Marshall had, but hopefully I can wow you with spectra. Okay. So outline of the talk, I'm going to start out by giving some background essentially on what we've seen of the population of super-Earths that we have detected so far, how this gives us some clues about their formation processes and how this kind of ties in to their interiors and their bulk composition overall. I'm going to lead into then really talking about atmospheres. What have we seen so far with the, well, right now, 2 super-Earths that we have observed their atmospheres. We're already learning some interesting lessons. And since this is a direct imaging meeting, I wanted to bring in a few thoughts on lessons learned for direct imaging as we think about how we might eventually look at these smaller planets via imaging and what that might take. All right, so I'm going to start with a similar slide to what Deborah Fisher showed yesterday, showing the history of planet detection starting back in 1995, where we only knew our solar system planets, and our single, very interesting hot Jupiter 51 PEG B. 10 years, or not even 10 years, 8 years later, we had our first 100 exoplanet detections, our first couple of transiting exoplanet detections, and astronomers were getting quite good at detecting Jovian mass, Jupiter mass planets. And now today, and this plot only has the set of planets that have well-constrained masses, or M sin I, and orbital periods. But okay, so why am I showing this plot? What's the takeaway point here? You could take a lot away from the population of planets that we now see. But for this particular talk, what I want to draw your attention to is the population of low-mass planets that has been uncovered over the last decade. So these are the super-Earth planets as our instrumentation has improved and our methods for detecting planets have improved. We've uncovered low mass and small planets. I should clarify some verbiage. When I'm talking about super-Earths here, I am typically talking about planets with masses between 1 and 10 Earth masses, or more generally, I'm really talking about planets with sizes and masses between Earths and Neptunes. We don't have any of these in our solar system, as you know. So this is one key reason why studying super-Earths is so interesting and so informative. We've uncovered a new population of planets that we really know nothing about because we've never seen one of these things before. Additionally, this has really important implications for planet formation, how planets form. Prior to the detection of exoplanets, we had this lovely picture of how our solar system forms. It breaks the planets very naturally up into these small rock and iron-dominated planets and these large giant planets made of gas and hydrogen, helium gas, and ices. And in our solar system, we also have this beautiful picture for why the outer planets should be the gaseous planets, the giant planets, and the inner ones should be the rocky planets. And clearly that's not what we're seeing with a much more diverse population of exoplanets. So perhaps a more typical solar system. This is what Kepler is showing us, is that there seem to be a whole bunch of systems that look more like this. So this is the Kepler 62 system. It has 4 super-Earths, 1 smaller rocky planet, all crammed into 2 orbits within the Earth's orbital distance. So we're seeing something really different here, and we need to understand what this means for the planet formation process and what these planets what are they? What are they all about? This is a quote that I really liked from Andrew Howard's science paper from last year. It's right in the abstract. And he says, the most common class of planetary system detectable today consists of one or more planets approximately 1 to 3 times Earth's size, orbiting within a fraction of the Earth-Sun distance. So these planets are incredibly common. It's very possible that the planets even smaller could be even more common. The true Earth-sized planets could be even more common, but that's still kind of on our detection threshold. But these super-Earths are common, and we can detect them now, is really the point. So if you look at the fraction of stars with planets versus both planet size and planet mass, what we have come to understand is that the occurrence rate increases dramatically with decreasing mass and planet size. There are a lot of these planets out there. All right, so again, what are they? You get a few hints from looking at the popular media and papers that have come out recently. We talk about water worlds and mega Earths and mini Neptunes and super Mercuries. So super Earths are extreme, and at least some of them are. And more importantly, they clearly have a whole range of different bulk compositions. They really cover the gamut. Okay, and we can see this in a more scientific way by looking at a mass radius plot. So mass or radius versus mass for the whole population of exoplanets that have both of these parameters known, and then we zoomed in on the super Earth population of planets off to the right. And if we plot the known planets over lines of set constant composition, what we can see is that the super Earths really do kind of fall all over the place. There are some trends that we can talk about, but there are planets ranging from more iron-rich than the Earth to water worlds, water-rich worlds, and hydrogen-rich worlds, which are the ones that we would refer to more as mini Neptunes. Just by placing the known planets on a plot like this, we can learn a bit about what the planets are composed of in the sense that some of these Kepler objects are clearly very rock and iron dominated, and there's some others that obviously their sizes cannot be explained unless you include a significant gaseous atmospheric component. But there's a lot of degeneracy between the different compositions because a pure iron or a pure rock planet, those are not the only options. You can have mixes of all the different materials: iron, rock, water, ice, and hydrogen, helium, gaseous atmosphere. So there's typically a whole family of interior bulk composition models that could fit any one of these planets. One thing that we do know is that if you fall above the line for a pure water-ice composition, then your density is so low that you must have a considerable hydrogen-helium atmospheric component, and then that does put you more in the mini-Neptune, scaled-down Neptune regime. And we've certainly seen quite a few planets now that seem to fit into that family, but it is not at all clear that there's any kind of sharp dividing line between the two. There's probably more of a continuum. We really kind of do have planets that cover the whole span, the whole range. Okay, so I know this is a direct imaging meeting, but one little bit that I want to put in about transits is these are a couple of results that have come out very recently and pretty recently. Having to do with how you can discern the composition of one of these low-mass planets from its radius alone, from its size alone. And the key point here is that as you increase in radius, you can change composition very dramatically. So basically, as soon as you pile on just a small amount of hydrogen, helium atmosphere, the size of your planet starts going up very quickly. So just by looking at the size of your planet, it's going to tell you something about the overall composition. This is a new, over here, this is a new result from Leslie Rogers that just appeared on AstroPH last week. And what she was looking at was the probability that a planet could be fit by a bulk composition that is rocky as a function of the planet's radius. And she sees this really sharp transition, essentially, at almost exactly 1.5 Earth radii. So the takeaway point here was that if you find a planet that has a radius that's larger than 1.5 Earth radii, that really should be considered more of a mini Neptune, a more gas-rich planet, and not a rocky super-Earth terrestrial planet. All right, Water Worlds was part of the title of the talk, and we've talked already about water-rich compositions. It's worth mentioning why we believe that very water-rich planets are a possibility, because we don't exactly see we don't see any of these water worlds in our own solar system. Earth is actually relatively dry, even though a large fraction of our surface is covered in water. We would be considered a relatively dry planet. But planet formation N-body codes show some really interesting things when it comes to formation of water-rich planets. So this is a result from Sean Raymond and his collaborators. And essentially what they did here, they started with a whole population of planetesimals. As you would expect, the water-rich ones start out beyond the ice line, out in the outer solar system, where water's going to condense. And as they allow the planet formation process to occur, so they allow migration and collisions and scattering and accretion to occur, after about 200 million years, they land themselves over here, where enough of the water-rich planetesimals have scattered inwards and have accreted on to inner planets, where we now end up with 3 large terrestrial planets that are quite water-rich compared to solar system terrestrial planets. So it's not, at least what this type of simulation is telling us, is that it's not unreasonable to expect very water-rich super-Earth planets in the inner solar system. And this fits what we seem to be seeing with the mass radius plots, the bulk density of many of these planets. All right, so what else can we learn about the overall bulk composition of super-Earths? This is a result from Jade Bond and her collaborators, looking at disk chemistry, essentially, around stars with different abundances. And what they found from their simulations is that you can build a very broad range of planets in terms of their overall composition with very different overall chemistries. So they get some very carbon-rich planets, carbide planets, more Earth-like planets, silicon-depleted planets. So they can really get a very diverse set of planetary compositions out of their simulations. All right, so this is the transition into atmospheres. So the planets are made of whatever they are made of, and it sounds like we could have a very broad range of bulk compositions. We can't directly probe the interiors of the planets beyond, measuring masses and radii right now. What we're stuck with observing is the atmospheres of the planets, but the atmospheres are clearly going to be tied into the overall composition of the planet. So the challenge with understanding the atmospheres, I think really the key challenge to understanding the atmospheres of super-Earths is that they're really, the processes that shape these atmospheres are really complicated. When you think of a gas giant planet, to first order, the atmosphere was formed by accretion of the gas that was in the disk when the star was forming, and to first order, that gas should have essentially the same composition as the host star, so mostly hydrogen and helium, and then you can argue about differential abundances of some of the heavier elements. But with the more terrestrial planets, it gets a lot more challenging because you're essentially talking about secondary atmospheres that were created via outgassing, and were probably heavily shaped by, or at least some of them will be heavily shaped by mass loss and atmospheric escape. So this is just a laundry list of some of the different properties or processes that could affect what you end up with as a final atmospheric composition. So the planet formation process that I was just talking about, the outgassing and the mass loss are probably very key, important processes to understand. The cooling history of the planet, perhaps the stellar cluster environment as the star was forming could be important. The chemistry, the equilibrium chemistry and photochemistry processes that shape the eventual molecular abundances of gas within the atmosphere are important, and the parent star spectrum is going to be highly tied into how the photochemistry proceeds. The planet's location relative to its host star and its temperature, the planet's surface gravity, and then whether there are plate tectonics or whether the planet retains a magnetic field are all going to play into the atmosphere that you eventually see and eventually observe, and one could give a 45-minute talk on any one of these items in the list. But instead, actually, you know what, this is a good place to stop for questions. Does anyone have any questions up to this point? Okay. We'll move on. So I'm going to talk to you instead about what we've actually seen so far. Given that, and I think this is kind of appropriate, given the broad range of atmospheric compositions and bulk compositions of these planets that we might expect to see, eventually this is really going to have to be, theory can tell us a lot, but theory continually is telling us that we might expect, again, a broad, diverse range of planets. So eventually we have to observe the individual objects and see what we're going to see. And this really is going to be a game of understanding some of these individual objects to then understand the population as a whole. So my favorite planet, maybe not yours if you guys are direct imaging people, you might like HR 8799 or some of those other planets. But this is my favorite planet, GJ 1214b. It was the first transiting super-Earth for which atmospheric observations were possible. Really, the first super-Earth for which atmospheric observations were possible. And the trick was that this is a planet that orbits a small, an M star, M3 or 4 star. So even though it's a small planet, it blocks out 1.5% of the stellar light during transit, which allowed observers to do the kind of atmospheric follow-up observations that previously had only been possible for Jovian planets. All right, and this is an interesting planet for quite a number of reasons, but one of them is that this planet is kind of just on the border in mass radius space where it does need a fairly considerable atmosphere to explain its low overall bulk density. So a number of scenarios for what this planet could be composed of were put forth. These are sort of n-member scenarios. So broadly, a first possibility is that this planet could be a mini Neptune. It could have some sort of rock ice interior with a hydrogen-helium-dominated atmosphere. That would fit very well, and that would be kind of the mini Neptune scenario. Alternatively, and more exotically, this could be one of these very water-rich planets where the planet is composed of a water ice interior with a very thick steam atmosphere. And then, of course, you could fall somewhere in the range in between. But so interestingly, we get to observe the atmosphere, and the atmospheres of these two scenarios differ broadly. So that was the name of the game. The slide is a little bit busier than I planned it to be, but let's break it down. So these are model spectra that I calculated in a paper with Jonathan Fortney right after the planet was discovered, and we were looking at what you might expect the observable signature to be if the atmosphere had different overall compositions, ranging from very hydrogen-rich, so essentially going with the mini Neptune scenario, to atmospheres that were composed of heavy molecules. Specifically, a water-dominated atmosphere would fit with the water world scenario for this planet. And as you can see, for transmission spectroscopy, the models look very different from one another as you go from the hydrogen-rich case to the water-rich case. The hydrogen-rich ones are all these ones with the big spectral features, and the water-rich atmosphere is one of these flat lines, the purple one, that just kind of looks very flat. This is an effect of the scale height of a water-rich atmosphere versus a hydrogen atmosphere. The atmospheric scale, so transmission spectroscopy is very sensitive to the atmospheric scale height because you're essentially probing the range of heights in the atmosphere over which the atmosphere becomes optically thick. So that's essentially that's essentially a probe of the scale height, and the scale height in the atmosphere it goes inversely proportional to that's supposed to be a mu, the mean molecular weight. So the mean molecular weight for a hydrogen-rich atmosphere is going to be 2 times the mass of the hydrogen atom, 2 AMU, and for water we're going to be at 18. So a factor of 10 higher in mean molecular weight means a factor of 10 smaller in scale height, so that the transmission spectroscopy features just get crunched down by a factor of 10. So this is a testable hypothesis. You should, with current instrumentation at the time, you should be able to see these big spectral features for the hydrogen-rich atmosphere, and you would expect to detect water features, maybe methane. Whereas if it was a water-rich atmosphere, you really wouldn't expect to have been able to see anything. All right, so that was the picture, and lots of data were taken. Yeah, there's some text that goes with this. There we go. All right, and so what was seen with a lot of data was very convincingly a very flat-looking spectrum. So great, hooray! Maybe we have detected a water world, a water-rich atmosphere, high mean molecular weight. Sure looks like the data are consistent with the water-rich hypothesis for the atmosphere. But it turns out that there's a sneaky alternative way that you can make a really flat transmission spectrum for one of these atmospheres, and that's just to throw in a whole bunch of clouds. Because clouds block out light or scatter light, and so you could imagine if you had a high-up cloud in your atmosphere, it would just essentially occlude any absorption of light that would happen lower down in the atmosphere that would have generated these large spectral features. So this is this nagging problem. Have we actually detected a high mean molecular weight atmosphere, a water-rich atmosphere, or is it just really cloudy? And Laura Kreidberg, in her beautiful paper, really put an end to this question. So with 15 transits using WFC3 camera on HST, very convincingly showed that the spectrum is so flat, so flat, that heavy molecule atmospheres are entirely ruled out. Water-rich atmosphere ruled out. CO2 atmosphere ruled out. So it's a cloudy world. That's the only thing that is left that fits between the data and the models. And before I move on to talk about the clouds, just point out that, that we recently observed a second benchmark super-Earth, HD 97658b. It has actually really similar properties to GJ 1214b. They're right next to each other on this mass radius plot. The key difference is the stellar host star. So the stellar host. So HD 97658 is a K star, whereas GJ 1214 is an M star, and there might be that, that might point to some real differences in the atmospheres of the two planets if photochemistry plays a key role and the irradiating spectrum of the host star plays a key role. So it's an interesting laboratory to try to compare the two planets against each other and see if there are any differences. So far, we have a couple of transits also using WFC3 on HST for this planet. And so the data are not, the error bars have not shrunk down to the point where we can make firm conclusions about clouds. But again, we see it's a little bit hard to tell, but the data are consistent with, again, a flat line. So the hydrogen-rich mini-Neptune scenario is ruled out, but the data are consistent with either a high mean molecular weight atmosphere, so potentially a water atmosphere, or alternatively, an explanation that would involve high clouds in the atmosphere. So it's something that hopefully with additional data we can sort out what's going on with this planet as well. So clouds, they've been a problem so far. We shouldn't entirely be surprised that we're seeing clouds, in a sense. And we look around the planets in our solar system, any of the planets and moons in our solar system that have reasonably thick atmospheres all have clouds or hazes. So these things are prevalent. They have different compositions depending on what the atmosphere is made of and the location of the planet relative to its star, but they're there. Many of this is actually, we were having a conversation at dinner last night that it might be a good idea to tell some of the grad students in the office some of the limits and constraints of some of the modeling work, some of the atmosphere modeling work that has been done to try to understand some of these planets. And actually, this is a key place to talk about this. So a lot of the models that people like me and others tend to show are often cloud-free models. And that's a good starting point, and it's a good first-order way to try to understand the atmospheres of these planets. Clouds are really challenging to model. It turns out that even for the Earth, we're not great at modeling our own clouds, and we live in the Earth's atmosphere. So clouds are a modeling challenge, but clearly we need to confront them in some way. And some ways that we do this is just by treating them in an ad hoc way, and you can just throw in an optically thick layer in an atmosphere, really not knowing what it is or why it's there. But we want to do better. We want to understand what these clouds are, what they're made of, why, what chemical processes lead to them being there. So this slide is showing a temperature pressure profile, a calculated one, for GJ 1214b's atmosphere, assuming a solar composition atmosphere. The temperature pressure profile was calculated without any consideration of clouds, by the way, so that's an important thing to know. But we've compared the temperature pressure profile just very simply against condensation curves for different, it's a little bit hard to see, but condensation curves for different molecular species that could condense in this planet's atmosphere. And the only notable ones that cross the temperature pressure profile, so hit the right temperature and pressure where these molecules would actually condense and form a cloud, are potassium chloride and zinc sulfide, which sound like probably very low abundance molecules, but it doesn't take a lot of any of these molecules to potentially make a cloud that could become optically thick in the transmission spectrum. They also appear a little bit, or quite a bit too low in the atmosphere in these models to really explain the observations that have been made so far, but there's a fair amount of wiggle room here because, well, as I mentioned, the temperature pressure profile shown here, the red one was calculated without any feedback effect of clouds. So obviously, once you form clouds, that's going to have effects on the temperature pressure profile of the atmosphere. And also, the condensation curves themselves can move around depending on the abundances that you assume for these different gases, and really for potassium and chlorine and zinc and sulfur. So the exact location of these lines really depends on the exact abundances that were assumed of solar composition for this atmosphere. So things can move around, and perhaps these equilibrium condensates could explain the clouds in the atmosphere. I mean, it works pretty well for Earth's atmosphere to first order, to say, where does water condense, at what temperature and pressure does water condense, and there are clouds. All right. Another possibility similar to clouds is hazes, where hazes would be essentially condensed particles that are showing up because of photochemistry. These plots are a little bit challenging to look at, but I'm essentially plotting abundances of different molecules as the result of a suite of photochemistry models where we've allowed atmospheric mixing to take place, as well as photochemical dissociation, so from the stellar incoming light from the top of the atmosphere. And a takeaway point is that relative to equilibrium abundances, we expect that particularly methane and ammonia are going to get depleted high up in the atmospheres of these planets, because those are two molecules that are very susceptible to photodissociation. And that's interesting from a haze formation standpoint, because when you break up methane, you get carbon that can then form into other molecules. It can form into higher order, very complex hydrocarbons, and those are known to be essentially hazy soot particles that could be responsible for a haze in the upper atmospheres of these planets. This is another avenue towards forming hazes or clouds in the atmospheres of these planets, and a little bit more challenging from the modeling standpoint to really understand the full chemical pathway all the way to hazes. I should mention that Caroline Morley, who's over here, has done some additional work that I did not include a slide on, but actually taking the opacities of some of these different hazes and the condensate molecules, and trying to understand what that would actually look like in the spectra of some of these planets, and would that agree with what we've seen so far? All right, so this is a kind of silly title, but a reminder: transmission spectra are not emission spectra. The point that I'm making here is that I've just shown you a whole bunch of results for transiting exoplanets looking at transmission spectra, but when you guys go out and eventually directly image planets of this variety, you're going to be looking at emitted light. And the geometry is different, and that could play an important role. So this kind of bleak picture so far, where we're seeing clear evidence of clouds in the atmospheres of these super-Earths, and it's giving us these really flat, boring spectra that we can't take a lot of interesting information away from. But also in transmission, we have to remember that because of the geometry, the starlight is coming through the atmosphere at this kind of grazing trajectory, and it's encountering a lot of atmosphere. And so it only takes a small amount of scattering particles to be present to have a big effect on the spectrum. That's not going to be as problematic for emission spectra, where the light exits essentially directly out of the atmosphere. So perhaps these clouds will be a little bit less problematic, even if they're very prevalent. Also, for emission spectra, you are looking at typically the day side of the planet relative to, or instead of the terminator of the planet, so a different part of the planet. So and you'll be looking at planets that are probably farther out in the solar system. So there's going to be some key differences that make me think that the picture is not really all that bleak, and the clouds are interesting in their own right. All right, so I'll spend just the last few minutes with some lessons learned for imaging. First of all, joking around at dinner last night that maybe some of you guys managed to achieve contrast of 10 to the minus 10 with your hands-on sessions yesterday. But I think, as someone who doesn't do imaging, I think that's pretty challenging to do. And the problem is that terrestrial planets, to image them, you need to get down to contrasts of 10 to the 9, 10 to the 10. So it's a really challenging game. One way potentially around that right now that I've been involved in looking at, so I want to just talk about briefly, is to think about looking at terrestrial planets during their formation process. And obviously this has worked well for giant planets. Look at young forming giant planets because they retain their heat of formation and so remain very self-luminous. It doesn't typically work so well for terrestrial planets because they cool down a lot faster. But there was an intriguing object detected a number of years ago now, and TMAS 1207b, and the idea was that this little guy over here was a little bit unclear what it was. Its temperature and its luminosity didn't really agree with the host star isochrones for if you assume this was like a giant planet or a brown dwarf. And so there was this idea postulated by Eric Mamajek and Michael Meyer that maybe this could be an afterglow of the collisional formation of a terrestrial planet, of a large terrestrial planet. So some simple math why you might want to look for these things. In a massive collision like the moon forming impact, you're gonna heat up your planet. You're gonna end up with an ultimate planet that has a molten surface, very high temperatures, up to 4,000 Kelvin. And typically you would expect that such an object in free space would just cool off essentially almost immediately by astronomical time scales. But you have to remember that when you have this molten planet that's been heated by this collision, you are going to be able to outgas volatiles from within the planet and form a new atmosphere very quickly. And so if you can form a thick atmosphere quickly, then the planet is going to radiate its heat away quite a bit more slowly, and it could retain its heat. It could retain a molten rock surface for up to maybe 10 million years. And if you do some quick back of the envelope math where, so let's see if I get this right. So if you have, if every star forms two of these rocky planets, and then each rocky planet has maybe two of these very large collisions over the course of their formation process, and then each afterglow takes about 2 million years to cool off. You're up to something like 8 million years per star per 100 million years or so of planet formation process time. So that leaves you with about 10% of young stars could maybe have one of these still hot, glowing terrestrial planets at a given time. So that's a little bit hand-wavy, but it makes the case that you might want to go look for these things. Okay, so we did some first-order modeling to figure out what you might see and whether it really would be worth looking for these things relative to the contrast that you might achieve with imaging, different imaging instruments. And the takeaway point really was that the atmospheric properties are going to matter a lot. If you manage to outgas a very thick atmosphere, that's great in that it keeps the surface of the planet hot for a long time, but it also means that you're going to radiate at a much lower temperature. So there's a trade-off there, a big trade-off. So we looked at atmospheres ranging from fairly thin to very thick, 1,000 bars. And then the composition of the outgassed atmosphere is going to have spectral windows at different wavelengths. So these are contrasts that are, were and are expected for different different direct imaging instruments relative to some of the contrasts over here that we got from our modeling results for atmospheres ranging from a bar to 1,000 bar for solar composition and Venus, so basically CO2 composition atmospheres. And the case looked not bad that, that you could expect pretty high contrast where you might actually be able to see these objects. You know, you probably have to survey a lot of stars, but you might get to see some of these things. Since then, I heard that Jonathan Forney, I heard, also presented a little bit about this, but I want to make some slightly different points. So more recently, a paper by Roxana Lupu and a whole pile of her collaborators came out where they did a much more sophisticated modeling job of trying to understand what the spectra of these collisionary afterglows would look like. And they have some similar results and some different results. So, okay, so over here, these are some of the spectra that they modeled. And they've done a lovely job of comparing to the models that I showed from my own paper in the previous slide, which are in the black lines right here. So you can see that, that my initial spectra made a much better case for being able to get high contrast out of these events because I was predicting these big spectral windows, these big bright spectral windows between the water features. And so this is another important modeling takeaway that I want to bring in here. So the models shown in the black lines were calculated for more simple atmospheric compositions, basically mixes of, so like the black line was a mix of water and carbon dioxide. We included, in our initial modeling, we included opacity, so something like 8 molecules. Some of the key ones that have opacities in the infrared: water, methane, CO2, CO, ammonia. So, you know, in a sense, what you put in is what you get out of the models. And these guys, in the newer paper, they included probably more realistic, but definitely more complex atmospheric chemistry. And along with that more complex atmospheric chemistry, they included opacity sources for something like 35 different molecules. And interestingly, when you include all the opacities of all those other molecules, you start to fill in some of the spectral windows. So in the end, they're predicting lower brightness temperatures in most of these windows where we predicted, you know, very high fluxes escaping. Keeps the planet hot for longer, but makes the direct detection case much more challenging. Where they still think that with 30-meter class telescopes, you might be able to image some of these objects depending on their atmospheric properties. But it's a little bit more of a bleak case for this. So the takeaway message on the modeling side is that it's important to understand the opacities that have gone into your models. I've recently updated all of my own atmosphere models with the same set of 35 opacity sources. But it's very important to understand what went into the spectral models in terms of opacities, because that can have really vast, important implications in what comes out the other end. All right, so I'm getting ready to wrap up. I just want to first bring up again my outline of my talk, but now in reverse to rewind through what I just said. So we finished up with some lessons learned for how you might think about directly imaging some of these super Earths in the near-term future. You have to do this via looking at, so you're going to be looking at the emitted light and the scattered light from the planet. So you're essentially, if you can take a spectrum, you're looking at the spectral information of the atmosphere itself. The atmosphere itself is very much tied in to what the overall planet is made of, the bulk composition of the planet. So by learning about the atmosphere, like in the case of GJ1214, if we found that it was a very water-rich atmosphere, that would have told us that it was also a very water-rich planet overall. And in turn, that is going to point to some really key aspects of how these planets are forming and really informing our picture of planet formation as a whole. And some more detailed summary points. I think, actually, how am I doing on time? Oh, okay. Well, I'll run through these points, and then it sounds like we have good time for questions. So super-Earths are planets that have size and mass intermediate to Earth and Neptune. We don't have any of these objects in our solar system, so they're very interesting laboratories for understanding the planet formation process, and they appear to be lots of them to look at. Hopefully we'll find more around bright stars in the near future with the TESS mission upcoming. They're a very diverse population of planets. The interior models have significant degeneracies, and therefore, by observing the planet's atmosphere, we can allow ourselves to differentiate between some of the possible bulk compositions for the planets, which is I specifically illustrated with the case of GJ1214 today. Direct imaging, on the other hand, leading into the real meat of this conference, is going to be a real challenge for terrestrial planets because they're small and they're cool and they cool off quickly. The collisional formation process might give us a window sooner into directly imaging these objects, but ultimately, future instrumentation, which is all of you guys, the grad students in this audience, who are going to be, hopefully building some of the next generation instrumentation. Hopefully some of that will ultimately allow us to take real images, pictures, amazingly, of terrestrial planets. Now I'll take questions. So the question is, how long could these clouds persist for? And if they're there, they could essentially stay put indefinitely. But it really depends on the process that forms the cloud. Water clouds in our atmosphere are going to be around for as long as Earth's temperature stays what it is and Earth's atmospheric composition stays what it is, and that can be long geological timescales. If you have patchy clouds, that might be that might be a nice way to get windows to look deeper into the atmosphere, like we see with brown dwarfs. And then viewing geometry could actually matter. Or maybe the patchy clouds kind of come and go. But for a thick, deep cloud layer, that could just blanket the entire planet essentially indefinitely. We see that in a whole variety of solar system objects. Venus, for one. We're not going to see the surface of Venus anytime soon. So the question is about the retrieval of the transmission spectrum of Titan from actual observations with Cassini, and so it was a real transmission spectrum of a planet, the moon, that we know a lot about, and they were able to see the sloping effect in the optical and the transmission spectrum of the Hazes particles that are there. So yeah, that's something that you can model. Again, by understanding the properties of the optical properties of the cloud particles themselves. So again, with Titan, we have the advantage that we pretty much know what the haze is made of. It's more challenging to do the reverse thing, where you don't know. You see evidence of a haze or a cloud, and maybe there is some sloping to the spectrum, but you don't know a priori what the cloud or the haze is made of. And then there tend to be families of models that can fit things, because you're dealing with Mie scattering, and you don't know the sedimentation efficiency of the cloud itself, and you don't know its composition, and these aren't like sharp molecular features. They're more like slopey or flat-ish spectral features that are just quite a bit harder to interpret. Is the problem. The spectra of GJ1214 was quite a variety of telescopes. So Laura Kreidberg's most recent result that shows that really amazingly flat spectrum, that's Hubble. There have been other Hubble data. There have been Spitzer data. There have been ground-based data from VLT and Magellan, and yeah. So it's been and there's other ground-based data as well. There's been a large campaign across many telescopes and wavelengths to try to understand that planet's atmosphere. So the question is about polarimetry of directly imaged planets and using polarimetry to understand the cloud properties. I think that is probably, yes, a key way to get at the optical properties of the clouds. I don't have a lot more to say about that other than it sounds promising. Yeah. So there's measurements of HD 189733 polarization measurements that are being taken and that's one of the planets that has strong evidence for Hazes. So yeah, it's being done for giant planets, or starting to be done for giant planets right now.